Welcome to my instructional video on how to do QR factorizations. There are several steps to doing QR factorization, and these are those steps. First, you must find the orthogonal basis for what you are given, which will usually be the image of A, or perhaps the span of a couple of vectors, and you do this via using Gram-Schmidt, which we will go over. Secondly, you must convert the orthogonal basis into orthonormal, which you do by dividing by its length, as we will show in the second step. And then finally, you can come to find the QR factorization. So in the first step, finding the orthogonal basis, as I said, you would be given perhaps let V equal the span of however many vectors you are given, which is also the same thing as letting V equal the image of A if A were perhaps these vectors put into a matrix. So the first thing that you should do is label these vectors x1, x2, and x3 so that you do not confuse them with V1, 2, and 3 as we are about to calculate. V1 is actually just x1, just on its own, nothing special done to it. However, we will be using V1 later to get V2 and V3. V2 equals x2 minus the projection of x2 onto V1. Now, this gets a little bit complicated to remember, but remember that if you're finding V2, it's x2 minus the projection of x2 onto something that you've already found. And thus far we've only found V1. So that's what we're going to be projecting onto. This equals x2 minus x2 dot V1 over V1 dot V1 times V1. And it's very important that you write these out so that you don't confuse yourself, or perhaps write down the wrong thing. I might even actually write V1 right here, add another step to it, but I'm running out of room here. But it might be helpful to do that on the test so that you don't make a mistake. And then here, I've just taken the dot products. I don't feel it's important to show that, because hopefully you would know how to do the dot products already. And once we calculate this, we get something that doesn't look very nice, but that is to be expected when doing the QR factorizations. And so here is V2. It's time to move on and try doing V3, which you start off by just writing the simple formula again, x3 minus the projection of x3 onto V1 minus the projection of x3 onto V2, because we already have V1 and V2. And that will be x3 dot V1 V1 dot V1 times V1 and again, I find it very helpful to write all of the dot products off to the side so that you don't mess them up. I already have them off to the side on a separate piece of paper here, which I don't feel it's important to clutter up the page with the dot products. And so, continuing this and adding in these dot products, we get minus 2, and then actually on this one over here, this is 0, which will happen sometimes. It means that this was already orthogonal. It's nothing to worry about. It actually just makes life a lot easier. And so In the end, that actually equals 2, 0, 0, negative 2, and that is your V3. And so for the final answer, sorry I can't be showing you that other page at the same time, we'll write V1, which is the same as the X1, V2, just as here, remember, write V2, not X2. That's a pretty common mistake sometimes. And then, oh, sorry. And then the V3. And so here is the orthogonal basis, and we can move on to the next step, which is finding the orthonormal basis. So this step is very important. It's often forgotten, I would think, and it's important because if you try to do the QR factorization with just the orthogonal basis, then it's not going to work. You have to turn it to orthonormal, which you do by dividing by the length, like that, to make them all of uniform length. And I've already done these calculations here. I have this one out just so that you can remember this is how you do it. But you divide this one by 2, this one by that, and this one by that, and once you do this to each of them, you'll get something that looks honestly a lot less nice, but that's to be expected. And now that we have the orthonormal basis, we can move on to the final step, finding the actual Q and R. So finally, now that we've found the orthonormal basis, we can begin to solve the QR factorization problem. Q is simply these vectors put into a matrix, so that's very easy. And R, you have to do a little bit of solving for. You use Q transposed, and you multiply that by A. And you'll have to remember A was all the way back in the first step. It's these 3 original vectors put into the matrix A. And really quickly we will multiply and find R to finish up the problem. So here we are at the final step of the problem, calculating R. I've gone ahead and written what we got for Q up here and the original matrix A from the first page up here. And simply what we do is multiply, which it may be tedious, but this one actually turned out rather well. I'm not going to bore you with actually multiplying it out. It would take up far too much time, but this is what I got for R. And now that we've solved this, we have finished the problem. I've gone ahead and written it on this page as well. So now that we have Q and now that we have R, we have finished the QR factorization problem. Thank you for watching. This has been a Stephanie Dykes production.